So the theory of a topological sort is this. Given a graph that has directed edges, does not have any cycles, and is a graph, but has logically ordered edges. So if we have an edge from U to V, it actually means there is some linear ordering in that, very similar to something like prerequisites for classes that you're taking. If that's the setup of the graph and the application, then we can do a topological order. Now, here's the interesting part, is that the graph already has the ordering in it, but it's ugly. We're going to end up changing really just the presentation of the graph, not the edges, not the vertices, so that frankly it makes sense to us. So we know the logical ordering of it. We also know what dependents there are for each node to be activated. It may need two other things to happen before it. So that's the interesting part about the topological sort. Now, here's the good news, is that we're going to be using something you know, and that's the depth first search, and there's going to be a twist, which I'll talk about here in a little bit. It is going to use recursion, and again, it has to be on what's called a DAG, that's a directed acyclic graph. So there's a lot of neat things about this in representation that, again, we're given blah, we're going to make it organized. And I'll show you what that looks like here in a second. So like I promised, here's the left-hand side of what the graph would look like, just totally disorganized. There isn't any cycles, which is hard to see, but there aren't any cycles. And again, it is directed. There's a reason to it. We're just actually converting it to this sucker right here, which in reality, it's actually the same graph as this one. The edges are all the same. The vertices are all the same. The only thing that's different about this is that this is showing us a logical order of how, well, they're dependents from our DAG.